Good morning. We're going to start, and this welcome section, and thank you to everybody that came also with this bad weather today. And I will give the stage to Gabriel Zutig, and for the welcome section.
Thank you, Alessandra, and good morning to everybody. Thanks for being here. Thanks for being connected online also. Today, the schools in Naples and province are closed due to the bad weather, but we're active. And it's a pleasure to open this final workshop on RePAIR, archaeology and technology. I would like to thank everybody who has made this possible, both the colleagues from the universities, but also the technical and administrative staff of Pompeii Archaeological Park. And special thanks to Alessandra Zambrano and Vincenzo Calvanese, who have dedicated a lot of time and energy to this enterprise. We have all learned a lot. I think it's on the one hand astonishing what can be done with technology and artificial intelligence. We have also learned that there are still limits where we can push forward. And especially for me, it was impressing how difficult it is to rebuild the human hand and to make it work like our human hands every day. And these are things you rarely think of when you act on a daily basis, touching things, lifting objects, restoring ancient objects. But it's actually a very complex interaction between touching, seeing, observing, even hearing. You know, if a fragment makes a slight crack, noise, then you immediately drop it and put it back on the surface. So all this has been an enormous challenge, and I think this is more than just, you know, playing around with technology as it sometimes could appear, because it's not. I'd say a race, and we are part of this challenge. Where on the one hand, we have fascinating new technological possibilities, especially thinking of AI and robotics and all that. But on the other hand, we also see that the modern technological progress, so-called, poses new challenges to our cultural heritage. And this too has become very evident in the RePAIR project. We are dealing with objects that partly were destroyed during World War II because of another technological invention, bombs that were dropped on Pompeii by airplanes. So this is kind of the other face of the technological progress, and today other challenges are being added to this. So not only the destructive voluntary destruction of cultural heritage, as in this case, but also climate change and the general urban development in this area. So archaeology really faces totally new challenges, not simply as a single event or episode, like putting together fragments. That has always been part of the work of archaeologists. But we're doing this now on a level, on a scale that has never been seen before in the history of humankind. Think of all the urban and infrastructure work going on. Think of the enormous quantities of data and objects that are found and have to be not only recovered, but also studied and made accessible. So for me, this is also a project about, and a workshop about accessibility and the democratic use of technology to preserve and study and make the cultural heritage of Italy and on a global scale available and accessible for the general public. So thank you all for doing this, and I wish you all a very inspiring conference.
Thank you. So now I give the stage to Professor Prota, as the new president of the Association for Engineering in Naples and Province. So thank you very much to come.
Thank you, Alessandra. Thanks for your work of coordination and organization. And I also like to send my greetings to Dr. Zutrigel for hosting this important workshop and for involving engineers of the province of Naples. I'm a new president because we just started our mandate on November the 3rd, and as a part of the board we have Vincenzo Calvanese. You know very well Vincenzo. He's an important engineer in this context of Pompeii. Actually we were very glad to recognize this workshop as part of continuing education for engineers of the province of Naples, because we believe that engineering is crucial also for the recovery and also for the assessment and interventions on the cultural heritage in general, archaeology, but also churches. Everything is the history of our nice country. And indeed, the presence in the board of Vincenzo Calvanese has a meaning, very clear meaning, because with him we really believe that we would like to strengthen the connection between engineering, I would say the STEM part, so engineering, architecture, geology, with social science and archaeology. Personally, I had I play my role of engineer at university, and I had an experience here a few years ago as University of Napoli, and I understand that this interaction that Dr. Zudiger was referring to is really the way to push forward if we want to follow the example of this site, which is, I think, is a reference in Italy, and I would say maybe in the world, because this connection between the archaeology, which is the main area of knowledge in this context, with the technology, can allow and can benefit to both. I remember experiences in Villa di Diomede or in other sites a few years ago where, as engineers, I am a structural engineer, with the colleague of archaeology, and the information that archaeology can share with engineering and vice versa could allow to strengthen some theories, but also to understand something. I remember, for example, that information about the thickness or the arrangement of tiles could allow us to recognize post-seismic techniques after the earthquake, before the eruption, and so forth. So in this case, today, we talk about the potential of using artificial intelligence, so IT technology with industrial technology, because I know that a robot has been built to give more potential to the archaeology and also to allow our citizens to enjoy these sites, and I think with this pilot project, other sites. So I'm very glad. I know that there are many colleagues also online, in addition to you that you are here. And today is also an important day for us, because at a certain point we will also deliver the certificates of attendance to a course that it was organized together with the Board of Architects on this topic of cultural heritage. So I think we go ahead together. I thank again for this involvement, and I'm sure that with the help and the support of Vincenzo Galvanese, our Ordine degli Ingegneri will be very present, if you want, also for future initiatives. Thank you.
Thanks. So we go on, and next was a plan for Lorenzo Capobianco, the president of our Architect Association, but unfortunately it was not come. So we go through with Engineer Dinardo, that represents here the Association of Engineers of the province of Salerno, and so I give him, so also we can use to.
Systematic monitoring activities can, on the one hand, provide increasingly in-depth knowledge of critical situations and vulnerability, and on the other, acquire the elements for rigorous planning of prevention, interventions, and control actions for landslides, erosion, and external stresses, which also include the presence of heavy visitor flows. In this perspective, the protection of archaeological heritage is closely linked to engineering issues, from the use of digital technologies for monitoring mapping to vulnerability analysis, to the assessment of natural risk, to the adoption of consolidation and disaster prevention measures. These are themes that engage the professional associations of engineers and the National Council of Engineers, which recently held some training seminar addressing the relationship between engineering disciplines and the management of cultural and archaeological heritage. This is the reason for the great interest shown in today's event by the Salerno Professional Association, which I'm pleased to represent on behalf of its president, Engineer Raffaele Tarateta. So I extend my best wishes to the organizers and participants. Thank you.
Thank you. So we go on. I introduce Dr. Luigi Oliva, that is director of the Institute for the Restoration, so Istituto Centrale del Restauro, and so I give him.
Thank you. I want first to thank the director, Gabriel Zuckriegel, for this invitation, and to all the responsible for the engineering and architecture organization. Well, just a few words about the very important occasion to participate to this workshop and to this presentation, because the Central Institute for Restoration has been involved in many works here in Pompeii, and is very very implied with the perspective about the restoring and conservation of cultural heritage. We were not part of this project, but we are very interested in it, and especially about the use of artificial intelligence, with which we are experiencing also in other projects, like some project about recognition for fractures on the tombstone in Pisa, or some other projects. And it's a very important occasion to understand which are the actual limits of this technology and which can be the perspective. In particular, I want to underline that nowadays we can consider the artificial intelligence to just now support the activities in conservation. But what is the real pushing on in this research is the fact that when we reach a good level that can be applied in some institution, in some occasion, in some situation, and will be tested, we will save a lot of time and a lot of money that will be the good occasion to let also all institutions, not only institutions that can pay a lot of money for that, but we can extend to all institutions this technology in order to make some important intervention on the heritage. And also we can also make this time valuable for other activities for the workers in this field, so that can be a shifting competence. And finally, which is a very important thing that I want to stress in this occasion, is that it could be another good way to link, to make the operators talk together, to put together people working in technology, the competence in technology with the competence in human resources and the cultural heritage, which is one of the most important intention in Central Institute for Restoration. So I'm very happy to participate to this Congress, to this workshop, and I thank you all for the attention.
Thank you. So now we have Professor Preilillo. There is the professor at the University of Venice, Ca' Foscari, and also is the RePAIR project coordinator. So he coordinated this project in these 4 years. Now is at home in Pompeii, and I will give him the microphone to talk about, give the welcome section, and also we'll continue with the technical session. We'll start with the RePAIR meeting.
Thank you very much. Good morning, everyone. And first of all, let me thank Dr. Zuchtriegel and also all the people in the Pompeii archaeological staff that for organizing this meeting. As you know, we are here to mark the end of the RePAIR project. And I have to say, I have mixed feelings because, of course, I'm happy that our project came to an end. But on the other hand, I'm kind of sad because after 4 years of intense work with meeting new people, new colleagues, coming here so many times, so Pompeii, I can say, is kind of my second home now. So it's very exciting on the one hand, but on the other hand, it's kind of sad because a very exciting experience came to an end after 4 years. The RePAIR project, as you know, dealt with a very challenging problem in the first place. It's the problem of physically reconstructing broken frescoes. And we try to solve this problem combining the most advanced techniques in the field of artificial intelligence on one hand, and also in the field of robotics, because one of the main goals of this project was not only to virtually reconstruct broken frescoes, but also to physically reconstruct it. So we try to combine both dimensions, the virtual AI dimension and the robotic dimension. And I have to say I'm kind of proud to say that this is one of the first projects of this kind in the world. So we were kind of pioneering this new technology. We were been talking before about the limits of AI. As you know, AI now is almost everywhere. It's difficult to find an area whereby AI is not being used somehow, even if we are not aware of that. And I have to say that this particular problem, as many other problems in the field of archaeology, are very, very challenging for us. Even using the most advanced technologies that AI has developed in the past few years, it's still a very hard problem. Now, sometimes, this project had a lot of visibility on the media, and many times I've been asked by journalists, friends, and colleagues whether one day we're gonna imagine a world whereby archaeologists, real archaeologists, will be replaced by machines, right? And actually, by the way, this is not the only project which tries to use AI in the field of archaeology. There are many others, not only projects that are being carried out here, and in the afternoon you will see some of them, but also in the world, AI is being applied in archaeology in many contexts. For example, for trying to discover new archaeological sites using satellites, or trying to translate ancient text or epigraphs, or trying to reconstruct virtually ancient destroyed cities and maybe navigating in those ancient cities. So archaeology is one of those fields whereby AI is being applied on a regular basis. And so, as I said before, sometimes people ask me whether one day will be archaeologists, real archaeologists, will be replaced by machines. Well, I have to say, I don't think so. Maybe this is a good news, because sometimes I've been asked this question with a pessimistic tone. Because what we learn, one of the things we learn in this project, is there is something which is very difficult to translate into a machine. There was a famous philosopher of science in the 20th century. His name was Michael Polanyi, who introduced a notion which I think applies very well in this context. He introduced the notion of a tacit knowledge. There are areas whereby we do things without being able to explain what we are doing, why we're doing that. We do things without being able to formalize what we are doing. And this has to do with the intuition, with many other aspects of the human mind, which is very difficult to capture from, with a machine. And I think that the problem we faced here in this project belongs to this region. Archaeologists do have and do use a lot of tacit knowledge, even physical knowledge, even to check whether two fragments match together, as we learned. Maybe they don't see whether they match. They feel it somehow. It's a physical feeling, which is very difficult to translate into a machine. So it remains a very challenging problem. I think that there is no risk, at least in the next decades, that real archaeologists will be replaced by machines. The right perspective for me is the following one. In the coming years, very likely, real archaeologists will be working together with machines as a kind of artificial colleagues. Machines have their own skills that men or humans don't have, and vice versa. So it's going to be a very fruitful and exciting collaboration. So I was very happy to be working for more than 4 years on this project, because I learned a lot of things, and in particular, I learned about these things, which make a big difference when it comes to the practical application, real-world applications of AI. So having said that, now we start the session, and maybe we can switch to my slides. Okay, here we go. So this is the title of the project, Reconstructing the Past, Artificial Intelligence and Robotics Meet Cultural Heritage. You already know what the project is about. It's gonna be, we worked on the problem of reconstructing physically broken frescoes. And first of all, let me mention that this is a project that has been funded by the European Union. We got 3.5 million euros for this project. The project lasts 4 years. We started in September the 1st, 2021, and we just ended a few weeks ago. And we are here today besides this workshop also because in 2 days, we're going to have the final review meeting. That's the final formal review meeting whereby the project officer from the European Union, together with the reviewers, they will come here and we will discuss with them what we have done, and they will, they will evaluate what we have done. And so the project involves 6 partners. University of Venice, the coordinator of this project. And then we have the Italian Institute of Technology, the Ben Gurion University in Israel, and then we have the Pompeii Archaeological Park, of course, the IST, Institute Superior Técnico from Portugal, and the University of Bonn in Germany. It was a very large, well, there are larger projects, of course, but this scale is also very, very good to work on a specific project. And there is a promotional video that we made at the beginning of the project which tries to explain what we have done. So let me first run this video and then I will try to explain what we have done in this project. There's also some audio. I will try and see whether it works. Sorry. So, oops. So you have seen basically the major components already in our project. So let me now explain to you what is the structure of this project from a technical point of view. There are 3 major pillars, 3 major activities we have done within this project. The first one involves the data acquisition and the modeling of all the fragments that we want to reconstruct. And so we created a database that, by the way, now is publicly available, and archaeologists all over the world can use, can visit, and can play with that. And secondly, which is basically the heart of the system, is the puzzle solver, because when it comes to the physical reconstruction of a broken fresco or a broken artifact, of course, from a conceptual point of view, it's like solving a jigsaw puzzle, which is much more difficult than the kinds of puzzles that we used to play. I'm going to say something about this later, but this is really the heart of the whole project, solving this very difficult puzzle. And finally, there is the physical dimension. Once the puzzle has been solved, then the robotic platforms will try to reassemble all the pieces together. So we had a vision, I would say, we had a dream when we started this project, which is, by the way, something that probably will happen soon, but not now. So basically, we imagined a situation whereby the archaeologists, after days and days of excavations, they collect a lot of fragments, a lot of shards, and they will put all those shards into a room, they will lock the door, and then they come next day and they will find all the shards reassembled together. This is not something that happens today, maybe not, it will not happen tomorrow, but it's very likely that one day, maybe in a few years, something like this is going to happen. And we are kind of proud that we started this vision. So let me say something about today's presentation. As you know, the whole morning is devoted, is dedicated to the RePAIR project. And so this section is basically split into 5 different talks. I will be talking about, in the first place, about the puzzle solver, the basic ideas, the basic conceptual ideas that we use for the solver. Then I will give the floor to Alessio Del Bue from the Italian Institute of Technology, who will be talking about the digitalization phase, how we acquire and digitalize all the fragments. Then I think we're going to have a coffee break. And then after the coffee break, Alessandra Zambrano will be talking about the role of archaeology in this project. One of the nice things of this project is that this is really an interdisciplinary project. We've been working with archaeologists day after day, and this was a very fruitful collaboration because we learned a lot of things, and I hope that archaeologists as well learn something from what we are doing. And then Plinio Moreno from IST Portugal will be talking about object manipulation. So the second part, the last 2 talks will be devoted to the robotic parts. So Plinio Moreno will be talking about visual perception for object manipulation. And finally, Niels Degler from Bonn University will be talking about our integrated platform that we built, and we're going to visit later on. Let me just anticipate, we're going to go there to our RePAIR lab after Niels' talk. And there's a bad news, by the way, because yesterday we had some technical problems. And so I think when we go there later, the robot is not going to work. So we're going to see the whole platform, but I don't think we are going to be able to see it in operation. Okay, by the way, if you are curious about this project, you can have a look at our website where you can find all the information, a lot of videos, a lot of technical information. So please go there. And also, if you want to use our social platforms on Facebook, on LinkedIn, and whatever. Okay, so now let me talk a little bit about the basic ideas behind the heart of the system, the puzzle solver. Which is actually one of the hardest things, one of the hardest challenges that we had to face in this project. So, as I said before, from a conceptual point of view, the problem that we tackled is like solving a jigsaw puzzle, much more difficult, as I said before, than the ones we used to play in our youth, or even now, because it's still a very entertaining activity. For several reasons. First of all, the number of fragments is usually, in a realistic setting, you have thousands and thousands of fragments, most of which maybe are very small, very tiny pieces. And maybe most of them do not belong to the same fresco, because when, say, building collapses, and maybe if in the building there are frescoes on all the walls and maybe on the ceiling, you know, all the pieces will be mixed up. So it's like you buy 4 or 5 jigsaw puzzles, and then you mix all the pieces together. You throw the boxes away, by the way, because this is another challenge of our problem. We don't know how the solution will look like. We don't have the picture on the box that will help us. And then you try to solve all these 4 or 5 puzzles at the same time. It's a formidable problem, even for a machine. Interesting enough, in the context of computer science and in the context of AI, because AI has a long history, although we've been talking about AI only in the past few years, but AI has a long history. It goes back even in the years before the first digital computers were created. So the first contributions in the field, they were given already in the 40s. And so people working in computer science and in the context of AI already started working on this problem already in the 60s. This is one of the first, if not the first paper which was written in the 60s. See, this was published in 63, a seminal contribution by one of the fathers of pattern recognition and AI, Herbert Freeman, who already in those years tried to solve this problem, tried to build an algorithm that tries to solve a jigsaw puzzle. Now, starting from that year, there's been a lot of interest around this problem. But interestingly enough, we saw a strange phenomenon here, because the very first paper, which we've just seen before in the 60s, tried to address the most difficult version of the problem. So basically unrestricted pieces. And since the problem is difficult, after a few years, people started working on simplified versions of the problem. And for example, people started working on how we can automatically solve commercial toy jigsaw puzzles. This version of the problem is simpler than the original one, which was tackled in the 60s. And then, starting from the 2000, people simplified the problem even more by focusing on square jigsaw puzzles. In this particular instance, the shape of the fragments, the shape of the pieces is always the same. They are basically little squares. And so we're going to just use color information to reconstruct the puzzle. Only recently, people started working on realistic scenarios. So there were a few papers starting from 2000. People started working on the real problem, trying to use AI techniques to reconstruct archaeological puzzles. When we start the project, the technology about jigsaw puzzle solving was already kind of advanced. In fact, here we can see how in those years before we started our project, algorithms actually developed by one of our partners from Ben-Gurion University, were able to solve very large puzzles. Here you can see an animation which shows how this kind of algorithms is solving large jigsaw puzzles of more than 3,000 pieces. And here it's even more challenging because here we are solving, this algorithm is solving a 10,000 piece puzzle. So when we started our project, we already had some algorithms which were able to tackle a very simplified version of the problem, though. And one of the things that we discovered was that the real problem is much harder than the usual assumption we make in our labs, right? Because this is what we found. Actually, this is an interesting video. We came here in Pompeii in 2018, and we wanted to meet the then director, Professor Osanna, to convince him to join forces. I still remember some of you were here, maybe, right? And so we tried to convince him, why don't we work together on this project? And they said, okay, just come with us, and we're going to show what we have. And they took us to the Casina Rustica, which is nowadays our lab, and they showed, look at what we have. Would you be able to solve this puzzle? Well, it was very, very, very challenging, because when we saw what they had here, it was something like, oh gosh, shall we make it or not? Well, it turns out that we didn't make it, by the way, but we made a substantial progress in that direction. The lesson is that, as usual, you know, real world is much more difficult than the lab conditions that you might work on in your safety or comfort area. So in order for us to solve our puzzles, we need to use a lot of cues, some of which are kind of obvious. Of course, the shape of the fragment is very important when it comes to the reconstruction, the color, the texture on the pieces. But we also learned other cues that usually archaeologists use in order to solve the same problem manually. For example, we learned that the back of the fragments might be also a very important source of information when it comes to the reconstruction of the frescoes, especially when they have these bamboo lines, which we're going to see probably later. Also the mortar shape and thickness, the repetition of motifs. There are many, many cues that we are kind of using for solving our problem. The problem was, how can you build a unified system that tries to use all these cues into a working system? And this is one of the contributions that we made in this project, I mean a scientific contribution. We exploited in our project a well-known principle in perceptual psychology, in cognitive and perceptual psychology. And basically, I don't know whether you are familiar with this, but for many years, the Gestalt school of psychology was also very popular in the context of art and art historians. The Gestalt school of psychology started at the end of the 19th century by Max Wertheimer, and it was a very important school of psychology which was very relevant for about 50 years in the 20th century. Other famous psychologists who worked in this area were, besides Max Wertheimer, who is one of the fathers, also Kafka and Köhler. Basically, Gestalt psychology tries to address the visual perception problems from a scientific point of view, I would say, trying to find the laws of visual perception. Their agenda and their vision was very ambitious. In much the same way as we have the laws of physics, which allow us to understand how the world works, etc., they try to understand whether there are laws behind visual perception. And they came up with some very interesting phenomena that actually we incorporated in our system. First of all, there is something that we are probably already familiar with, our basic innate instinct for patterns. That's a very important aspect that Gestalt psychologists knew at the outset. We open our eyes and we don't see just patches of color, but we see objects in 3D. And we see things even when there is nothing, right? We see, for example, the sky in the night, and we see constellations. There are no constellations, of course. This is something that we built on the real data. Or we see, you know, shapes in the sky. So there is an instinct. Our visual perception system has an instinct for patterns, to the point that we see patterns even where there are no patterns. There are a lot of visual illusions around, which clearly shows that we are always looking for patterns, even if there is none. For example, on the left-hand side, we probably see a triangle, a white triangle. This is called the Kanitsa triangle, but there is no triangle. This is a visual illusion. But our first impression is that there is indeed a triangle. Or here, we can see a line, a curve, actually, but there is no curve. This is something that our brain superimposes on the data, on the visual data. And one of the things that that Gestalt psychologists did was to discover perceptual grouping laws. And these are the kind of laws that we use and we are using in our puzzle solver. For example, here are some examples of how things work. Let's focus, for example, on these little dots over here. Here, no grouping takes place. Probably if I ask you what do you see here, probably you will tell me, well, I see 6 dots, period. But if I move some dots around, for example, I move this dot a little bit on the right, and this dot a little bit on the right, maybe this one a little bit on the left, then you will see that spontaneously we see a different thing. Of course we see 6 dots, but now they are kind of grouped. We see 3 groups of 2 dots each. So our brain somehow is looking for patterns in the data, is trying to group things together. And this grouping phenomenon, you can see it's present not only for proximity, because here the dots are always the same, they are black dots. What changes here is just the distance. But also if we change the color, for example, if we keep the distance between the dots the same as here, but we just change the color, white instead of black, we see another grouping phenomenon. We see 3 different groups, 2 are white and 2 are black. If we change the shape of the dots, we always see some grouping, and so on and so forth. So this is something which happens all the time. We don't know why this happens. Neuroscientists are trying to understand why this happens, but it happens all the time. And the same is true not only for dots, but also for curves. Look at what happens on the right. Once again, there are 6 curves there. But if I ask you to tell me what you see, probably you will tell me that you see 3 different groups. And probably you will tell me that this is one group, this is another one, and this is another one. So there is a natural tendency for grouping. Same story, why this is the case? Because they are parallel curves. So it looks like that parallel structures have some role in our brain when it comes to visual perception. Another variable which plays an important role is symmetry. Once again, here you see 6 curves. Yes, there are 6 curves, but there is some symmetry in this picture. And you will probably see this as a group, this is another group, and this is another group. So these are the kind of laws that Gestalt psychologists studied and introduced in their seminal studies in the first half of the 20th century. It was a very tremendous impact, not only in psychology, but also in computer vision, because when computer vision started in the 60s and in the 70s, a lot of these ideas were imported into computer vision. Now, there is one principle, though, that Gestalt psychologists introduced in their work, which plays a major role when it comes to puzzle solving. And this is the principle of good continuation. Let me show what it means with a simple example. So here you see 2 curves which intersect at some point, right? Now, if I ask you to describe those 2 curves, to describe what you see here, probably you will tell me that you see this, right? You see 2 curves. One is basically this one, and the other one is this one. But if we think about this, this is not the only possible interpretation. In the first place, the fact that there are 2 curves is our own assumption. There might be 4 curves, for example. Why not? There might be curve number 1 from here to here, curve number 2 from here to here, curve number 3 from here to here, and curve number 4 from here to here. So why 2 in the first place? But somehow our brain thinks that there are 2 curves which intersect at a point. But even if we are convinced that there are 2 curves, well, why not this? Why not a curve which here is green, which starts from here, gets here and then goes back, and here there's another curve which starts from here and goes back. This is another possible interpretation. So you see what happens. There is one visual stimulus, which is there. And our brain has a number of options. 2 curves, the first option, this one, second option, third option. There are many, many options. There are many, many possible interpretations. But somehow our brain systematically chooses one, chooses the one in the middle. And this is because of the principle of good continuation, because somehow our brain, our visual system prefers smooth curves. There's a tendency for our brain to prefer smooth curves. So we wanted to incorporate this principle in our puzzle-solving algorithm because we think that it is precisely this principle that allows us, humans, to solve our puzzles, our jigsaw puzzles. When we try and see whether two pieces go together, we are implicitly or explicitly using that principle to solve our puzzles. So one of the contributions of this project when it comes to the problem of puzzle solving was to, for the first time, incorporate this explicitly, this principle in our puzzle solver. And we see here what happens. There are 3 examples here whereby, yes, shape might be a good clue. Color might be a good clue. But sometimes good continuation is the clue that you are using. Look at this example. Take these 2 pieces, piece number 1 and piece number 2. As far as shape is concerned, well, probably they don't match at all. There's just a little portion that, for which there is some intersection. But actually, why do we think that these 3 pieces go together? Well, because of good continuation. Because there's this pattern over here, which continues smoothly over here, and this continues over here. So there are many, many things like this. When it comes to archaeological puzzles, basically, we constantly see the use of this principle. So that was one of our contributions in this project when it comes to puzzle solving. For the first time, we noticed and we incorporated this principle in our algorithm. There's a second contribution, though, which is also novel and innovative, and we think might be a good starting point also for further research, which is the use of game theory. Because now that we identified this principle, the good continuation principle, as an important clue when it comes to puzzle solving, now we have the problem of building a computational framework for solving puzzles using this principle. And so we thought that game theory might be the right answer to the problem. Now, game theory was invented, literally, many years ago by one of the greatest scientists of the 20th century, John von Neumann, who was a mathematician, he was a physicist. He was one also of the fathers of computer science. Our students, we say to our students that our computers use a von Neumann architecture. So one of the geniuses of the 20th century. Among the things that he did was the invention of the theory of games, which he invented literally in the 20s. As the story goes, he was a poker player, and for that reason he wanted to understand how he could make more money using more theoretical ideas. He was a great mathematician, so for that reason he invented game theory. By the way, this is a legend, I don't know whether it's true or not. What happened is that in the 20s, John von Neumann published a paper which played a seminal role in the establishment of the field. And interestingly enough, this is also very common in science, more or less in the same years, another mathematician, a French mathematician this time, Émile Borel, independently from von Neumann, published another paper in French this time, while von Neumann paper was in German. At that time, scientific papers were written in national languages, introducing more or less the same ideas as von Neumann. So we see that at the same time, 2 great mathematicians introduced more or less the same ideas, but von Neumann made a step further. After about 20 years, von Neumann published a book which became the Bible for economic and social sciences for many years. The theory of games and economic behavior. He wanted to use the theory of games that he invented from scratch to solve economic problems and social problems. But the problem was, with his theory, that the kind of games he addressed was very restricted. Technically speaking, these are called zero-sum games. But the real world is more difficult than that. So the next seminal contribution was given by John Nash in the 50s. in his PhD thesis, a very short one, by the way, just more than 30 or 40 pages. In that little PhD thesis, he made a substantial step further in the theory of games. He introduced the notion of the Nash equilibrium, for which he got a Nobel Prize many, many years later. By the way, probably you have heard about John Nash because of a beautiful book and also a movie whose title was A Beautiful Mind, which appeared a few years ago. This is going to be very important for our story because this notion of a Nash equilibrium plays a key role in our system. Well, something also, from our perspective, something interesting also happened later in the 70s when a biologist, a very well-known biologist, John Maynard Smith, used game theory to solve problems in biology, and then he invented evolutionary game theory. For us, this is very important because this gave us the algorithms for solving our problem. I'm going to skip these slides because we don't have time and it's kind of technical. I'm going to just go to the basic idea. How can we solve a jigsaw puzzle using game theory? Well, it's very simple, actually. You have a set of fragments, a set of pieces, and these are the players, quoted, unquoted, of the game. And you have a set of possible positions and orientations. And these are the strategies, right? So basically, the problem is to assign to each piece, which is a player, a strategy, which is a position and an orientation in the plane. And there is a beautiful theory which allows us to claim that the Nash equilibria of this game are exactly the solutions of our puzzle. There is one problem that we need to address, of course, which is what is the payoff function that we use in game theory. And for our own problem, the payoff function is basically something which relates to the compatibility of two fragments. It's a measure which tells us whether two pieces in a certain position and orientation match well. The higher the value, the higher the compatibility, the higher the payoff. So once we formulate this in terms of a game, we can use the algorithms coming from game theory to solve the problem, and this is exactly what we did in our project. And here is an example whereby this is our real fragments in the Casina Rustica that we found there. This is the result of a very recent paper. You see, 2021. I told you that the problem is difficult. 2021, this is one of the state-of-the-art algorithms before we start the project on archaeological puzzles, and that's the solution that the algorithm gave. Because this algorithm is not using good continuation. It's just using shape and color, which here doesn't work. And this is what we got with our own algorithm, right? Using the good continuation principle, we managed to solve this little portion of the puzzle. And this is an example which shows how the matching occurs. Of course, the problem, since we try to address a large-scale problem, requires also the intervention of archaeologists. So we basically built a system which allows archaeologists to be in the loop. So our system basically works in the following way. The system, the archaeologist or the system identifies some anchor piece around which the puzzle will be constructed, basically what we do typically when we solve our TOEI jigsaw puzzles, right? We start with some piece and we try to expand the puzzle around that area. Then we detect possible neighbors, because of course in the presence of thousands of pieces, we'd better choose a subset of neighbors. And then we run the algorithm. The algorithm very likely will make mistakes because the problem is difficult, and then we allow the archaeologist either during or after the process to intervene to correct mistakes, for example, or to give suggestions. And of course, this can be done before to choose the anchor fragment or during the process by correcting the process when it starts providing wrong solutions, or after the process, when the process ended, we allow the archaeologists to intervene. I have a short video which shows what happens. Let's see, it's a long one. I'm gonna skip some parts. So here is an example of how the system works. The archaeologist chooses one fragment, this one, that's the anchor. So now the puzzle will be built around this piece. This is what the algorithm is doing, is trying to put the pieces, the neighbors, around the fragment. The level of transparency that you see is related to the confidence that the algorithm has, because the algorithm gives also some confidence about the positioning of those fragments. So now the archaeologist or the expert selects the right ones. In this case, I think there are 2 or 3, I can't remember. He or she accepts it, and now the process starts again. So this becomes a kind of meta fragment. We are no longer breaking that fragment into further pieces. And so now the algorithm will start. Let's see, it takes some time. Let's move in other pieces around. Maybe I will skip this. And here we go, the second loop, in the second stage, after the human intervention, the system tries to fix the other pieces. Now the archaeologist intervenes to fix the right ones and to throw away the ones that are clearly wrong, until eventually the puzzle will be solved. One of the things we did in this project was also to build a data set of more than 1,000 fragments. We presented this data set last year in one of the major conferences in machine learning. This is the RePAIR data set. And so now this allows us to test on a quantitative basis our algorithm. And so here you see there is a measure, a quality measure that we introduced, which ranges between 0 and 1. 1 means perfect, 0 means a disaster. And this is what happened on the data set that we built with the existing algorithm, and this is what we did in the project. This is our RePAIR solver, which is still unsatisfactory, of course, because the problem is difficult. I'm not claiming that we solved the problem. On the contrary, we just started. But at least we managed in a few years to substantially improve the state of the art. Now, what you see here is the RePAIR system without human in the loop. So just the result that the game theoretic approach gives us. Of course, with human intervention, the result is much better. So with human intervention on a small set of pieces, we are reaching much, much better results. Interesting enough, we don't reach 1, which is perfect, because the problem is difficult even for archaeologists. Sometimes it's really difficult to solve them. Okay, I think I will stop here, and thank you very much for your attention. If you have any question, of course, I'm here. If not, we can move on with the next speaker, who is Alessio. Thank you very much. Thanks.
Okay, great. So, hello everyone. Thank you, Marcello, for the presentation and for hosting us today here in Pompeii. So, I start presenting you one of the initial problems we had in the RePAIR project. That was actually to create a digital replica of the fragments you see in the previous slides. As you can understand, this was one of the major challenges we had, because the puzzle solving approach that works in this digital space need a description of the pieces that we are gonna assemble all together. And this replica has to be the most accurate as possible. So we had the challenge that in Casina Rustica, we have really thousands of these fragments in the area you see. So this try to make a catalog of these pieces is, of course, a task that has taken the time of archaeologists. But indeed, the challenge we had is to find an easy way to digitize all these pieces in the area of the Casina without, of course, moving the pieces from where they are. And indeed, our task was as well to assist the archaeologists in creating a digitization device that was really affordable to use and also that was able to solve this task we had. So this is the Casina Rustica here in Pompeii that was remade thanks also by the RePAIR project. And as you've seen before in the video of Marcello, we have really a huge number, I think more or less like 16,000 of pieces all stacked inside the Casina. And here you see the scale of the number of pieces we had to attack for the 3D digitization process we started to do, where you see that it goes from very small fragments to wider ones. So one of the first study we did is to statistically understand the size of the pieces inside the Casina. And the subject of experimentation, of course, it was the frescoes, where small fragments of wall mosaics from the House of Painters at work in the Archaeological Park of Pompeii. And indeed, we couldn't move the pieces from the place where we had, so we had to bring the digitization device inside the Casina. So one of the constraints was indeed to create a setup that was easy transportable. And so our requirements in the beginning when creating this device was indeed to have a system that is relatively cheap, of course, and easy transportable, so to do essentially field work, so to move from one area and the other, and of course to remove it back when it's needed, and also to achieve a high level of details. Okay, the details you can achieve, of course, can be even to the microscopic level, but indeed we needed the level details that was necessary to solve the puzzle solving problem, but also to provide to the archaeological park a digital replica that was really enough even for catalog work, so to keep a digital copy inside the park. And as well, as I said before, we needed to scan a range of sizes that was enough to deal with all the pieces, fragments we had inside the archaeological part, and also being non-destructive, of course. We didn't have to manage any one of the artifacts inside Pompeii. So this is just show you a glimpse in the video of the system we created. Indeed, you see that the 3D scanning process provides an information on the 3D size and or the texture of the objects, and is created by these black boxes where we have a system with the structural light that is able to extract this 3D information from the pieces. And you see the system in action. It has a rotary table that rotates the pieces and takes different pictures and 3D scans that then are subsequently merged all together in a single 3D representation. And also we are able to attach high quality textures in order to use this texture information as well for the puzzle solving problem. So the system is really, the one you see here is not very big, so it can be inserted in any space where the artifacts are. We thought, of course, when it constructed, to place it in Pompeii, but this is a general device. It can be brought to any other spaces to do the 3D scanning task, and is very simple in its composition, because we wanted to have a simple system. It's a lighting box that reduces the external illumination, and turntable, that is the device that turns the pieces with the fixed stepwise degrees, and a higher resolution HB camera to achieve a very good texture for the task I told you before, and a 3D scanner sensor that is actually taking the 3D images with the sub-millimeter accuracy for the pieces. We devised two setups, one with the single box and another one with the two boxes to reduce the time, where one had the 3D scanning and the other the texturing with a standard camera. So each of the equipment was able, for the single box, to have a capture time that was around 9 minutes for the first setup per piece, and the reduced time for the two boxes setup of 5 minutes, which was a good timing given that we had to both capture the 3D structure of the piece and the texture in it. The data acquisition and digitization overview was the following. It's a completely automated step, so we wanted to have a system that just the archaeologist can put the piece on the rotary table, press a button, and the system does that, the scanning totally automatically way. So indeed, we have a part where we have the SCADI platform that has both the RGB camera and the 3D scanner. From the RGB images, we are able to extract a set of images of the piece rotating. From that, we can extract both the texture, high quality, and a coarse 3D shape just from the images. This information is used then to align both the information from the camera and the 3D scanner. Instead, for the 3D scanning, the only other step the archaeologist has to do is to put upside down the object, because we need a scan from the upper part and the down part. So having two scans of the bottom and top, we have to align them all together, so to fuse together the 3D point clouds in order to reconstruct the 3D shape. Then we fuse together with texture mapping both the higher resolution images we have from the camera and the part related to the 3D scanning. So this was enough to manage to produce a data set that Marcello has mentioned before, more than 2,000 total fragments, which is one of the most populated data set for this type of problems in the literature. And there was that's the reason that was very well received by the scientific community, but also one of the most extensive catalogs for this type of problems in the fresco reconstruction. So these are the groups that we were dealing first, because we had already a solution with that was a manual solution performed by archaeologists from the University of Lausanne. So we had sort of what we call the ground truth. So we had the puzzle already solved, for which we can compare the automatic methods for puzzle solving that Marcello has previously shown to us. So in this we had both the 2D version of the puzzle, so only the texture, and the 3D version with each pieces in 3D. We have also related metadata, which is useful for the archaeologists, that is related to the artistic type, weight, digital size, dimension, the bounds of the pieces, and the geometric transformation that solve the puzzle as done by the archaeologist. The ID, of course, which is the catalog number that is useful for the registration of the pieces and the catalogs, the texture maps, the groups, and the acquisition data and file names. Of course, this metadata can be further refined given the standard standard classification of catalogs. And this is just by showing you some of the solved puzzle by the archaeologist. This is the images that we are taking with the camera, but you see, you can see in Casina Rustica, this is the 3D reconstruction of the puzzle with all the pieces well aligned in 3 dimensions. And here you see all the singular pieces, how they look in 3D, in the digital version. This is for another more extensive puzzle. This was really necessary for assessing how well the hardgrains can reach the puzzle solving skill of the archaeologist. I have to say these problems are really complex, and you see it here because you have erosion of the pieces, because the fragments, of course, when they fall from the walls, they hit the floors and they've been eroded and broken in little more pieces. So the automatic algorithms, they have the problem to understanding these missing gaps inside. And this one is for another, of course, pieces. This is nice because also the 3D copy can be used to create as well 3D printed copies, physical copies of the objects. So this concludes my talks. If you have any questions about the 3D scanning device, please let's have a follow-up. And I have to thank you as well, Theodore. That is a postdoc in my group that highly contributed in the scanning and in the of the device. Thank you very much.
Okay, we are going to have a break. Also, then the ceremony, because there are some engineers that have to award their professional credits and so the diploma for a course that was here, was made in the last 6 months here in Pompeii. So we continue also for the streaming in half an hour. It's okay. So now it's 11:09, so probably 11:40. It's okay?